Bismillahirrahmanirrahim. About a few seconds, we'll go ahead and start. So let's wait until it's 10:22. Okay. Bismillahirrahmanirrahim. Welcome to E21. So today's lecture will be our 11th lecture, and in this lecture we're going to continue talking about mesh current method. So we introduced mesh current method last time. And in this lecture, we're going to continue talking about special cases associated with the mesh current method. In particular, is the notion of a sober mesh. Then we'll talk about a difference between node voltage and mesh current methods, since we've covered both. And finally, we'll start a new analysis technique, and this technique is called source transformation. So just going over the logistics, we're going to have a quiz inshallah on Wednesday, and the quiz will be during the class time. The instructions are exactly the same as the instructions for quiz 1. However, the coverage will be different. So it's going to be chapter 3, 3.1 to 3.4, and chapter 4, 4.1 to 4.4. Basically, chapter 3 and node voltage method. Okay, so in the previous lecture, we talked about another systematic way. So if you remember, we had this big circuit that we wanted to solve for the essential mesh current. We noticed that if we solve directly for the mesh current, for the branch current, for the essential branch currents, we're going to end up with a huge system of equations. In our case, it was 7x7 equation, which wasn't bad if you do it in a computer or something like this, but it's not an efficient way. So we stated that if we introduce a new intermediate variable, this analysis or this system of equation is going to be reduced. So we started with the node voltage method, and in the node voltage method, we noticed that, well, the number of needed equation instead of being BE, which is the number of the essential branches, is going to be the number of essential nodes minus 1. It's always the essential nodes, the number of essential nodes is less than the number of essential branches. So this implies that we are reducing the number of equations. In the last lecture, we introduced another technique. Instead of introducing a mesh current, instead of introducing a node voltage, we are going to introduce a mesh current variable in each mesh. And this is going to reduce the number of equations from BE to BE minus NE minus 1. So we introduced this notion, and then we went and discussed what happened if we have a dependent source. We realized that having a dependent source does not change anything, except the fact that we need to add an extra equation that constrains the dependent source, the value of the dependent source. So the number of equations is increased by the number of dependent sources. And the last thing that we discussed was what happens if one of the mesh currents is actually is a current source. So we have a current source that's equal to the mesh current. We noticed that, well, the number of unknowns is reduced because basically we found one of the mesh currents. So this is the first special case. Now let's talk about the other special case. So if you recall in the previous special case, the situation we had was something like this. And we have a big circuit. So this current source was this current source is equal to the mesh current. So this current source basically in the perimeter of the circuit. So what happens if we have a current source in the middle of the circuit and we're trying to apply mesh current method? So if you recall, when we talk about node voltage method, we had a situation similar to that. But remember, node voltage method relies on solving KCL, and mesh current method relies on solving KVL. So with the node voltage method, we had the situation where we have two essential nodes, and between them we had a voltage source. So we said that if we want to solve for the node voltage, we're going to introduce extra number of equations, and then we need to do some sort of substitution, and then we'll end up with the right answer. However, we noticed that this is kind of like a long journey to the final answer. So we decided to go for a shortcut. So the shortcut was by introducing the notion of a supernode. So we're creating a huge node, a huge essential node that actually covers two essential nodes. So we have two essential nodes, and there's a voltage source between them. So we said, well, let's combine these two essential nodes along with the voltage source and create one big node. And this node is called supernode. And we're going to apply KCL as it is, in a similar manner to a standard node voltage method. In the case of the mesh current method, we're going to have the same situation, because remember, mesh current is simplified when we have a current source. Now, if we have a current source in the middle of the circuit, then, or between two meshes, the issue here is that we cannot directly find the voltage across, because remember, eventually we're trying to apply KVL, so we need to find the voltage across it. So we cannot find the voltage across it. So we can do some sort of substitution, something similar to what we did with the supernode. But it turns out that if we create a huge mesh and mentally eliminate this current source, just keep it in mind, just mentally eliminate it, and solve for KVL inside the circuit, we're going to end up with a simplified approach to solve the problem. And this big mesh is called a super mesh. So these statements might be a bit confusing, so let's discuss it with an exercise here. So let's try to solve the mesh currents here. We have IA, IB, and AC. Let's try to find IA, IB, and AC. So a standard way, what you usually do is the following. So you start with so if we apply the mesh current method in loop A, so we're going to apply KVL plus 3 IA minus IB plus the voltage across the current source. We don't know the voltage across the current source. We can label it V plus 6I. So we're trying to apply the mesh current, the KVL here. So if we simplify it, we're going to get 9A minus 3IB plus V equals 200. And this is the first equation. So what about the second equation? So the second equation is going to be, by this time, we are all familiar with, hopefully, we are all familiar with the mesh current method. So we're going to apply the mesh current method in the in loop B, this one. So we're going to have 10 IB plus 2 IB minus IC plus 3 IB minus IA equals to 0. So if we simplify it, we'll end up with minus 3IA plus 15 IB minus 2 IC equals to 0, and this is the second equation. The third equation is going to be also straightforward. So we're starting here. So we have minus V, the voltage across the current source, plus 2 IC minus IB plus 50 volts plus 4 IC equals to 0. So if we simplify it, we'll end up with minus 2 IB plus 6 IC minus V equals to minus 50. So you notice here we have 3 mesh currents, IA, IB, and IC, and we have something, we have to find the voltage across the voltage source, across the current source. So we need to eliminate V. Abdullah, question?
Yes, Doctor, in IC, why is the voltage in the current source negative?
Because we set the polarity for that. So we set the polarity for the current source to be something like this.
So it is positive with the voltage rise. If the current is with the voltage rise, the voltage will be positive, and vice versa.
No, we're setting things up here. We're assuming things. So we're assuming the direction of the current source. So we have to be consistent here. So if we assume the direction of the current source this way, then we have to consider it when we apply KVL in loop A and KVL in loop C. So we cannot just flip the direction.
Okay.
So we can see here that the fact that we have a voltage source, the fact that you have a current source requires additional equation. So we need somehow to eliminate it, substitute 3 into 1, and this is going to give me some sort of simplification. Then I need to relate IA to IC, and you see that, well, it's eventually you're going to get the right answer, but this is not a systematic way. Remember, our goal is to construct a systematic way of solving for solving the mesh currents. So it turns out if we eliminate this one, so we take this one, we eliminate it. We say, okay, we're going to remove it mentally. And let's draw the circuit without the current source. So in this case, so let us use a sober mesh. So let me draw the circuit here. So 10 ohm. I have 2 ohm here. Then I have 3 ohm here. I have a 50-volt source here. I have a 4 ohm here. And I have a 6 ohm here. And I have a 100-volt source. So what I'm doing here, I'm creating some sort of a big mesh. So this is IA, this is IC, And I have this kind of like, okay, let me use different color. This mesh here. So I have a bigger mesh here. That's why we call it super mesh. And in this case, let's apply standard KVL here in this super mesh. So let's apply mesh current and method. Okay. So this is going to be minus 100 volts. So we're starting from this point, plus 3 IA minus IC. Then we move to the second mesh, 2 IC minus IB. This one IB. Plus 50 plus 4 IC. Now we moved back to the first mesh, plus 6 IA equals to 0. So we have an extended, we have a mesh current, we have a KVL that covers two meshes. So if I simplify it, I will end up with 9 IA minus 5 IB plus 6 IC equals to 50. This is the first equation. So the second equation is going to be exactly the same as the previous equation that we used to find. We used to apply KVL around mesh 2, around mesh C. So it's going to be 10 IB plus 2 IB minus IC plus 3 IB minus IA equals to 0. So if I simplify it, I will end up with minus 3 IA plus 15 IB minus 2 IC equals to 0. So you see here that now we have two equations from the mesh, from applying the mesh current method. But here I have 3 unknowns. So what should I do here in this case? So I need what I need to do is actually I need to Shabab, I'm going to explain it. So unless you have a question, please go ahead. So the last, because I cannot solve this system. This system has infinite number of solutions. So in order to find a unique solution, so I need to go back and relate the current source to the mesh currents here. So simply by applying KCL. So I have IC here. This is IC. This is IA. And this is 5 ampere. So what I can do is from KCL, I have going back here, IC is entering or simply minus IA plus IC equals to 5. And this is the third equation. So I have 3 equations, 3 unknowns. So I can construct the solution for the problem. And I can do that 50, 0, 5, 9, minus 5, 6, minus 3, 15, minus 2, minus 1, 0, 1, IA, IB, IC, And if I solve for it, I will get IA equals to 1.75 amperes, IB equals to 1.25 amperes, and IC equals to 6.75 amperes. So any questions, Shabab? Is the idea clear? Hadi?
Doctor, and the equation 3, can we use the positive determinant for the current source to obtain equation 3?
You mean on the top?
Yes.
You mean here?
Yeah.
Yes. If you do that, you will get actually you will get IA and 5 entering the node. IC is leaving the node. So you will get exactly the same.
Okay. Thank you.
Any other question? Okay, let's solve this exercise. Karim, question?
Yes, doctor.
Yes.
And the question 3 here from KCL, isn't IB there also, like IA, the current source, and also IP?
Oh, yeah, the thing is like here. Oh, okay. Here's the thing. Yeah, this is a very good question. Hadi, going back to your question, actually, the best way to apply it here is to use this node here, because you have IC and IA. You don't have IB.
Oh, got it.
Okay. Thank you, Abdulkarim, for pointing this out. Yes, if you want to apply it here, then you will have the superposition. Well, anyhow, IB will be common between them, so you can subtract it out. But anyhow, maybe this is the best one. So IB will be also common. So any other question? Okay, no more questions? Okay, let's go ahead and solve. Okay, in this exercise, we are asked to use the mesh current method to find the power dissipated in the following circuits. And the power dissipated in the 1 ohm resistor in the following circuit. Going back to this is just to remind me of something. You will see here that Hadi, this current source is between the mesh currents IA and IC. So it should be a function of IA and IC. It shouldn't be a function of IB. So this will be, if you apply in KVL, this will be the total current IC minus IA. Okay, back to the exercise. So we're asked to find the mesh current method. We're asked to use the mesh current method to find the power dissipated in the 1 ohm resistor and the following circuit. So we have a circuit here, and we are asked to find the mesh current method. So how many meshes do I have here? Yes, sir.
Yes, so we have the special case here, so we can consider 2 meshes. We can combine the top one and the bottom left one.
Okay, so where is the super mesh here?
The super mesh is between the bottom left mesh and the top mesh.
Okay, this is the super mesh. This is the place where we want to remove the current source. So we have a current source. So let me just write it down. So we can use the super mesh technique or the approach. So let me call this one IA. IB and IC. So if I draw the circuit, it will be something like this. This one is 2 ohm, 2 ohm, the reverse polarity here, 6 volts, 1 ohm, and then we have this connection. So I'm just labeling the mesh currents here. I have IA, IB, and I have IC. Okay, Mohammed Al-Sweden, can you apply the mesh current method in the solar machine?
Yes, it will be minus 100.
Okay, actually not 100, this one too. Okay.
So it will be minus 10
Mhm.
plus 2 IC plus IA.
Plus 2 IC plus IA. Are you sure?
I think.
It's 2 IC actually.
Right, it's 2 IC, right. Then 2 IC minus IB. Then 2 IA minus IB. It equals to 0.
Okay, good. Very good. So if I simplify it, I will get 2IA minus 4 IB plus 4 IC equals to 10. This is the first equation. Adnan, the second equation.
2IB minus IA.
2IB minus IA.
2IB minus IC.
2IB minus IC.
Minus 6 volt. Plus IB.
Plus IB equals to 0. So if I simplify it, I will end up with minus 2IA plus 5 IB minus 2IC equals to 6. And this is the second equation. Ibrahim, the third equation.
Can you go back to the original? It is IA equal to 2 plus IC.
IA equals to 2 plus IC, exactly. So in this case, IA minus IC equals to 2. And this is the third equation. So I have 3 equations, 3 unknowns, so I can easily solve it. So I construct the matrix 6, 2, 2 minus 4, 4, minus 2, 5, minus 2, 1, 0, minus 1, IA, IB, IC. So IA will be 7 ampere, IB will be 6 ampere. IC will be 5 ampere. But remember, this is not what we are asked about. We are asked to use mesh current method to find the power dissipated in the 1 ohm resistor. So this is the 1 ohm resistor. Wael Kuzi.
Yes. We would substitute in the power equation.
Yes, what is it?
B يساوي I squared multiplied by resistance.
Which is 1.
It would be 36 watt.
Okay, exactly. So I here in this case is 6, which is IB. Just remember this one. IB squared. Okay, excellent. Okay, we see that this application did not add anything new to us. The only thing that it does is actually simplifies the calculation. It significantly simplifies the calculation. So now let's take another exercise, and this exercise is one of the most interesting exercises for a reason that we're going to see in a moment. So we're asked to use a mesh current method. We asked to use mesh to find the mesh current IA in the following circuit. We have IA. Let me call this one IB, and this one IC. Muhsin, question or you wanna participate?
Participate.
Okay, go ahead.
Okay. Minus 25.
Okay, Muhsin. Here's the thing. Just look into the circuits. Just see what's going on here before you proceed with the solution.
We have 2 current sources.
Yes. And what about these 2 current sources? What are they?
I didn't know.
Okay. Ziad?
One is dependent and the other is not.
Yes, but what information can we infer from these?
That we know the current, the bigger mesh.
That which one? Bigger mesh?
Loop. The whole loop.
Okay, you kind of hit it then. Okay, Salman?
I think IC equals to minus 10.
Okay, yes. IC equals to minus 10. Okay, what else, Omar?
And IB is equal to 2 V node over 5.
Exactly. So we can see here that although we have 3 equations, 3 meshes, it turns out that 2 of them, we have a current source in the perimeter. So the value of the current source equals to a constant, say like here plus or minus, the mesh current here. So the problem can be easily simplified. So instead of just directly applying mesh current method, you see that the problem is simplified by noting that the branch currents are the same as the mesh currents. The branch current sources. So therefore, we have IB equals to 2 VP divided by 5. IC is actually minus 10 amperes. So you see here, the problem is much simpler. So it only involves one equation, one unknown, plus the fact that I have a dependent source which kind of like which adds another extra equation. So let's try to solve it. So let's apply the mesh current method and the first circuit and the first and the only mesh that we don't have. We don't know the mesh current. We don't know the mesh current adds. Ahmed al-Nafi.
We solve IA.
Yes.
Minus 75.
Mm-hmm. Okay.
Plus 2 IA minus IC, which is minus 10.
So 2 plus 10. I'm sorry, A plus 10.
Yeah, A plus 10.
Mm-hmm.
Plus 5 IA minus IB, which is 2 V naught over 5.
It's VP now.
0.
Okay, good. Very good. Okay, excellent. So let me just write it down. So minus 75. I write down exactly what you said. IA plus 10 plus 5. IA minus 2. VP divided by 5 equals to 0. So if I simplify it, I will get 7 IA minus 2 VP equals to 55. So this is the first equation. I still have two unknowns. So I have IA and VP. Ahmed al-Hamad. How to find a relation between VP, another relation between VP and IA.
The second mesh or what?
How to find the relation between? So now we have two equations, one equation, two unknowns. So we need to find another equation in the circuit that relates VP to IA. Okay.
2V over 5 is IB.
Okay. طيب,
2V over 5 is IB.
Okay, that's not gonna help us. So let's Hassan aside.
Yes, doctor.
How to find another relation that relates VP to IA.
You will find the equation of the second mesh. You will.
I don't need to apply the second equation for the second mesh. There is a direct way. Fahad?
By applying the mesh for current B.
No, you don't need to apply the mesh for current B. So, okay.
Parallel the battery with the 75 volts.
They're not in parallel. So let's move to Muhanna.
Maybe I just use Ohm's law on
Exactly.
the 5 ampere resistor.
Yes. So how to apply Ohm's law here? That's exactly what I'm looking for.
V equal IR, and I here will be A1 minus I1 minus IB.
Exactly. So applying Ohm's law. So if we apply Ohm's law here, we can see that, well, sorry, if we apply Ohm's law here, we see that the current passing for the 5 ohm resistor is going to be IA minus IB. We know IB, which is 2VV minus 2VV divided by 5. So it's going to be VV IA minus 2 multiplied by 5. And this is going to give me VV equals to 5 IA minus 2 VV. And if I solve for it, or if I simplify it, write it in the standard form that we usually use, we have 2 equations, 2 unknowns, so we can easily solve for the unknown values. 5 minus 3. And if I solve for it, I will get 15 ampere. VV equals to 25 volt. And remember here, I was asked to find IA, which is 15 ampere. Okay, very good. So we saw that. We consider 2 scenarios. The first one is we need to apply directly super mesh. The second one is actually we saw that since we have 2 current sources that are equal to the mesh current, so the number of equations is actually reduced. So if you did not notice this, then you're probably going to end up with 4 equations and 4 unknowns. Actually more than that, so you need to do some sort of elimination. Okay, Rahim, question? Abdullah Yusuf, question? So if you don't have any question, please lower your hand.
دكتور
حسن.
لو كملنا باستخدام طريقة المش هل بنوصل لنفس الجواب ولا ما يمدي؟
لا.
بس بتكون أطول.
بتكون أطول.
تمام.
Okay. Because eventually what no, you cannot. Here is the thing. No, you cannot. Because you don't know the voltage across the voltage source here, the current source. So remember, when you apply the mesh current method, you're trying to actually apply KVL. So you need to know the voltage across this voltage source, or this current source. So you don't know that. Abdullah Al-Jariri.
Doctor, if the current on the mesh on down on the right, if it was on the opposite, would we need to reverse all the loops, or do we just make it negative?
Which one?
The IB, if the current was on reverse to upwards.
Well, I always like to do it clockwise, in a clockwise direction, but it doesn't matter at the end of the day, as long as you're consistent with the way you apply things.
Okay.
So it means that if you want to reverse the direction of this, you need to actually be careful when you apply the mesh current and mesh A as well. Okay, Al-Hamdani, I need to move very quick, Shabab.
Okay, Doctor. So, what's the key to use mesh method? So that the thing that when I see it, I directly use the mesh method.
Okay, you're talking about the thing that we're going to cover in a minute. Okay, so moving to the the comparison between the node voltage and mesh current method, this will answer your question, Aziz, is actually let's pause and let's compare the mesh current method with the node voltage method. So remember, we introduced two techniques, and we said like those techniques are going to simplify our analysis to the circuit. They're going to reduce the number of equations needed to solve for the branch currents by introducing intermediate or by introducing intermediate variables. So let's compare the node voltage method with the mesh voltage. Actually, this one should be mesh current. So for the node voltage method, it's KCL driven method. It means that all the time we're trying to apply KCL at all essential nodes. However, if we're talking about mesh current method, we just had a few exercises on that. We saw that we're trying to apply KVL, not KCL. So the node voltage is KCL driven method. The mesh current method is a KVL driven method. We saw that the presence of the voltage source between two essential nodes. So this one is the node voltage method relies on the essential nodes. So if we have a voltage source between two essential nodes, the problem is simplified. On the other hand, when we talk about mesh current method, if we have a current source on the mesh, that simplified the calculation. We saw that when we talk about node voltage method, we need the number of essential nodes minus one equations. This is assuming that we have independent sources. If we have a dependent source, then we need to add constraint equations. If we have a mesh current method, we're going to have the number of essential branches minus the number of equations needed to solve the node voltage method. And this is going to give us the number of equations needed to solve the mesh current. So you may ask yourself at this stage, which method to use? You have a circuit. Is there a strategy to choose one method over the other, or should I choose them randomly? Sometimes in the exams, you will be asked to use a specific method. And in this case, you don't have any other option. But sometimes you will have an option to choose which method to use. So in this case, you ask yourself, which method has less number of equations? This is very critical. If you end up with, say, like you solve with mesh current method, you end up with 6 equations. And if you solve with node voltage method, you end up with 3 equations, then definitely you should go for node voltage method. Do you have a super node? Do you have a voltage source between 2 essential nodes? Then you may need to choose, say, like in this case, they both have the same number of equations. If you have a super node, then in this case, you may choose a node voltage method. If you have a super mesh, then in this case, it means that you have a current source between meshes. Then in this case, you use the mesh current method. In all of these cases, what you need to do is you need to spend time and think about the approach before you start. Unless you're told to use the following approach, just pause a few seconds and think about which approach to use before you proceed with the solution. Let's analyze this issue with the following circuit. Ziad?
When it says a voltage or a current source, do they mean an independent, or it doesn't matter, just if it's dependent, add one equation?
It doesn't matter whether it's independent or dependent, because whether it's independent or dependent, you know the value. Okay, so let's illustrate what I was saying with the following circuit. So we are asked to find the power dissipated in the 300 ohm resistor and the circuit shown below. So we have this circuit, and we see that in one method, this circuit is easily solved, while in another method is kind of like complicated. So the first step is actually choose which method to use. So let's compare these two methods. Okay, let me make this side for the so the left side. So the left side for the node voltage method and the right side for the mesh current method. So for node voltage method. So let's see what we have. So I need to identify the number of essential nodes. So I have this one, this one, this one, and that one. So what I have is, let me call this V1, V2, V3. So I have 4 essential nodes. This is going to give me 3 equations. So I'm trying to evaluate which one of them. And also, like, I have one source, which is in this case, this source. One source is connected between 2 essential nodes, between a reference node and another essential node. And this source is going to reduce the number of needed equations by 1. One source is so in total now I have 2 equations. So in total, what I have is the following 2 equations from node voltage method and 1 equation from dependent source. So in total, I have 3 equations and 3 unknowns. Okay, this is what happens when we apply the mesh current, when we apply the node voltage method. So let's see what's going on when we apply the node voltage method. When you apply the mesh current method. So we need to identify the meshes. So I have IA, IB, IC, ID, and IE. So I have 5 meshes, which means that I have 5 equations. I have 1 equation from dependent source. So this implies that I have 6 equations. So now I have 6 equations. But I notice here that the dependent source depends on one of the mesh currents here, which is IE. So I notice that IE equals to minus I delta, or I delta equals to minus IE. So this kind of like gives me a direct one-to-one relation between the constraint equation and one of the mesh currents. So in total, I have 5 equations. So what do you think? Which method should I use? One will give me 3 equations, the other will give me 5. Simply what? The one that's going to give me 3 equations. So simply the mesh current, the node voltage method is the method to use. And if we apply the node voltage method, we can actually simplify the calculation. So I'm not going to solve this exercise. It's actually in the book. You can refer to it. But what I'm going to tell you is we need to use node voltage method. And the result is we are asked to find the power. The power is 16.57 watts. So this is again in the book. You can refer to it. One more thing here. Your textbook has another, I think, 2 or 3 exercises. One of them is the mesh current method is easier to solve. So you may need to refer to this, or you definitely need to refer to this exercise. So does that answer your question, Aziz? Hamdani?
Yes, doctor, definitely. But I think it will need more practice.
Practice, yes. طيب. Okay. Now we're going to shift gear and just pause and think about what we did. So if you recall, all of the techniques that we studied, which are 2, mesh and node voltage and mesh current method, we are attempting to simplify the or introduce some sort of like a systematic way, a fast and systematic way of solving the circuit. We haven't touched the circuit itself. So we did not simplify the circuit. We simplified the calculations, but we haven't done anything with the circuit. So just let me write this one. Previous methods. We simplify the calculations. Following this method, the method that we're going to use is actually we're simplifying the circuit itself. So instead of keeping like a big circuit and solve it in a systematic way, we're going to simplify the circuit and solve it either in a systematic way or like just a standard Ohm's law, KVL, a simple KVL or KCL. So this requires some sort of notion of source transformation. So what do we mean by source transformation? So a source transformation, so oftentimes we have a voltage source and current source, right? And when we talk about voltage source and current source, we want to find a way to move between these sources. So say like you have a voltage source in series with the resistor, something like this. So what you want to do between the terminals A and B, you want to create another circuit or find an equivalent circuit, but instead of having a voltage source in series with a resistor, you will have a current source in series with a resistor. And you want to make this transformation bilateral means that you can start from one and go to the other, or vice versa. So if I call this one ix, I need to ensure that ix is here, the same value. So this requires finding the value or the expression of is and relate it to vs and r. Meaning that if we assume this is the starting point, then what I need to do is I need to create an equivalent circuit, but instead of having a voltage source in series with a resistor, I'm going to have a current source in parallel with the same resistor. And this equivalent circuit is going to guarantee that the same current between the terminals A and B. So how it relates to Vs and R. So let's try to derive it. So let's imagine we start with this circuit and we have the following we have a load RL. And we want to connect RL to this circuit, the voltage source in series of resistors. So I have Vs, I have R. Again, this is A, this is B. So let me use different color here. This is RL, and I want to find the current here, IL. So what is IL here? So this is simple Ohm's law. IL will be Vs divided by R plus RL. So this is the current. So now what I want to do is I want to see what happens if I use a current source in parallel with the resistor. So I have the following scenario here. So I'm going to do the following. I have IS, this is R. I'm going to connect the same load here, A and B. And so let me see. And I want to find IL. So in order to find IL here is simply current divider law. So I have R divided by R plus RL equals to IS. Let me call this one 2, this one 1. So what I want to do, I want to ensure that this transformation, moving from this circuit to that circuit, guarantees the same current, the same IL. So what value of IS should I use to ensure that this relation holds? So for 2, to be the same as 1, I need to set IS to be VS divided by R. So this is a very important observation. So what it tells you is the following. It tells you that VS AB is equivalent to VS divided by R this one is A, this one is B. So what did we do actually? What we did was, I said like, well, we want to make sure that if you do this transformation, if you have a voltage source in series with the resistor and you convert it to a current source in parallel with the resistor, the current supplied to the load is not going to change. And it turns out that this condition is going to hold if and only if the current source is, if the value of the current source is the value of the voltage source divided by the resistance. Okay, is it clear, Shabab? So you may ask yourself here, why did we do this? How is it going to help? And this could be explained with the following exercise. So what we want to do, we want to find the power associated with the voltage source here in the following circuit. So we can see that we can apply node voltage here easily. We can apply mesh current easily. But let's apply some sort of source transformation. Let's simplify the circuit. And in order to simplify the circuit, we need to have a resistor, 6 volt, and whatever comes here. So what I want to do eventually, what I want to do is 6 volt or Vx. So I want to simplify everything here as I want to find Vx and R for everything. So what I need to do is I need to do some sort of source transformation here. So let me start with the, first of all, I should avoid touching this one because I need it. I should avoid tampering with it because I need it. Nafi, question?
I need to solve.
No, hold on a second. I need to.
Okay.
I need to. Okay. So what we can see here that we have a resistor in series with the voltage source. So I can replace it by a current source in parallel with the resistor. So what's the value of that source? Is going to be the voltage source divided by the resistance. So 40 divided by 5 is 8. And remember here, the direction of the current is following the direction of the voltage here. So the current is entering from the negative side of the voltage source and leaving from the positive side. So if we reverse the polarity, then the current will be reversed as well. So in this case, I have 6 volts. So the 5 ohm used to be in series with the voltage source. Now it's in parallel with a current source. and the value of the current source is 8 amperes. So notice here, because I have, in this case, I have 5 ohm in parallel with the 20, so the parallel combination is 4. So this allows me to simplify the circuit. So I will end up with 6 volt, 4 ohm, 30, and 6.
الدكتور نسيت ال 10 اوم.
دائما سهل. So, good, thank you.
Welcome.
So this one is 8 ampere. Okay. So you can see here now what other source transformation that we should use.
From the
So
current source.
yes, so we have a current source in parallel with the 4 ohm resistor, so we can convert it into a voltage source in series with the 4 ohm resistor. So the value of the voltage source now is going to be 8 multiplied by 4, and the resistance will be in series. Okay, so now I need to combine the 4, and again here the 10, I forget it. So I need to combine the 4 and the 10, 4 and 6 and 10, so the combination will be 20. And in this case, I have 6 volts. Okay. Now a question.
الدكتور الحين اللي بين 6 وال4 وال10 in series.
Yes, they have the same.
بس الفولتج سورس مو معقل الموضوع.
لا. Okay, now I have 32 in series with the 20, so I can convert it to a current source in parallel with the 20. So the value of the current source is 32 divided by 20. And in this case, I have 60 volts for 30, 20, and 1.6. So now I can see that I have 20 and 30 there in parallel. So the parallel combination will be 12. I have a current source, so it will be something like this. So you'll see that in the following exercise, inshallah next class, that we're going to skip some of these steps. We're going to do more than one step at once. But for the sake of illustration of this exercise, we're going to do things in details. So now what I have 12 ohm in parallel with the current source. So I need to convert it to a voltage source in series with the resistor. And the value of the voltage source is 19. Okay, now it's simplified. So I'm assuming, because this one has higher potential, so I'm assuming that the voltage is, the current is flowing from 19 to 6 volt. So the current, I need to find the power. So I need to find the current. So the current will be 19.2 minus 6 divided by 16. And it's going to give me, which means that the direction of the current, I'm getting a positive value, which means that the direction of the current I assumed is correct. So the power of the 6-volt source is going to be 0.825 multiplied by 6, which is 4.95 watts. And we have this source is absorbing power. So the 6-volt source is absorbing power, is not generating power. Any question? Yes, Ahmed. That's it for today. Can leave if you want.
الدكتور عندي سؤال بسيط. الحين لما حولت ال current source اللي ب 1.6 شلون اعرف ان ال 12 اوم احطها فوق ولا تحت؟
It doesn't matter. It's all in series.
اي بس مثلا لو تجيني مسألة ثانية.
It really doesn't matter. It's all in series. So if I tell you the following, if this one is 4 ohm, this one is 6 ohm, will the circuit be different if this one is 6 ohm and this one is 4 ohm?
No.
Okay, it's exactly the same thing.
Okay. Thanks.
في واحد برضه سأل. Okay. Another question. Okay, if you don't have any question, we'll see you inshallah tomorrow.